Okay, so here we've got the notes for section 3.1, the derivatives of a function. So we've got our objectives as usual. So understand the meaning of the derivative, calculate the slopes and the derivatives using the definition, and then graph the function f from the graph of f prime, graph f prime from the graph of f, and blah, 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 blah. Okay, so down here we've got the definition. So the derivative of a function f with respect to the variable x is the function f prime, whose value at x is given by this equation, provided the limit exists. So what this is doing is it's moving some point closer to f of x, and h is measuring how close the values are. So it's kind of like we talked about the slope sliding something closer. Same thing here. Okay, so the domain of f prime may be smaller than the domain of f. If f prime exists, we say that f has a derivative that is differentiable. Well, that should be italics f. A function that's differentiable at every point is a differentiable function. So example one, find the derivative of this. So we're going to use this definition of here. So f of x plus h minus f of x all over h. Take the limit as we go to 0. So got the limit as h goes to 0. So f of x plus h is just this equation with x plus h plugged in for x. So x plus h cubed, and then f of x is just x cubed, the original equation, all over h. So a quantity cubed is the same thing as having 3 copies of that quantity. So that's just expanding the cubed. And this is a FOIL, and then I have to distribute again. But I'm not going to show all that work. I'm going to end up being x cubed plus 3x squared h plus 3x h squared minus x cubed. So this stuff here is the FOIL from, or the distributing from that all over h. So if you notice, my x cubes cancel. So limit h goes to 0 of just 3x squared h plus 3x h squared all over h. So coming up here, if you look down here, I have an h in all the terms, so this h can cancel that and one of these out. So I'm at the limit, h approaches 0 of 3x squared plus 3x h. And so if h is 0, that becomes 3x squared plus 3x times 0, which is just 3x squared. So this equation is f prime of x, the derivative of this original equation, x cubed. All right, so here we've got an alternate definition. So this is, instead of letting h get measuring 0, so you're letting your distance between your actual point and your secondary point get closer and closer and closer. What this is doing is it's essentially putting some second point on top of the first point. So differentiate root x using the alternate definition. So let's give this guy a try. So we've got the limit as x approaches a. So f of x is just my original equation, so root x minus root a, all over on the bottom, x minus a. So what I need to do is I need to get rid of these roots. So what I'm actually going to do is I'm going to use what's referred to as the conjugate, which is the same thing except with the sign in the center different. So plus instead of the minus here. So when I multiply across the top, that's a FOIL. So root x by root x is just x. Root x by root a, so plus root ax, since they're both underneath the root, they just multiply together. The middle terms here are going to be minus root ax, and then it's going to become minus a all over. Now on the bottom, I'm not going to FOIL because I'm cheating, and I know what's going to happen in this problem. So I've got this. If you look at these middle two terms, they cancel out. So limit x approaches a of x minus a all over x minus a times root x minus a. Whoops, that should be a plus down there. Plus, there we go. So look like that. These two terms cancel. This x minus a can cancel that x minus a. So we've got the limit as x approaches a, so just 1 on the top because you got canceled out. On the bottom, root x plus root a. So if x is approaching a, that means that these are the same thing. So I can replace this a with an x because I want it to be an f of x, not f of a. So, or I guess we can use a. So as x approaches a, this becomes 1 over root a plus root a. So 1 over 2 root a. Or if you want it in terms of f of x, f prime of x is equal to 1 over 2 root x. So there you go, alternate definition. Either one doesn't really matter which one you use. I prefer to use the first. Okay, notation. So all 4 of these things mean derivative. So y prime is pretty common if you have a y, if your equation is y equals. F prime, the one we use up here, is if you have an f of x equals, we'll use f prime. If you have a y equals equation, it's y prime. Because remember, y and f of x are the same thing. Dy dx, you'll see this sometimes written if you have equation in terms of y, df dx, f, and then this here, d over dx, this is actually the derivative operator. So d over dx means take the derivative of this, f of x. The variable on the bottom here is what variable you're taking the derivative of. If you have a multivariable equation, you have to specify which one it is. All right, example 3 down here. Relations between the graph of f and f prime. So graph the derivative function whose graph is shown in 3.3a. Oh, that's just down here. I didn't label it. Discuss the behavior of f in terms. So it wants us to graph the function. So 2, 4, 6. So here, for example, so 2, 4, 6 will count up. So when x is 0, the slope is 4. So that'd be there. Here at about 1.5, the slope is 1. At 2, the slope is 0. At 3, the slope is -1. Whoops, down here. At, what is that, 5? The slope is also -1. And at 6, the slope is back being 0. So essentially, instead of using x and y, I'm using these slopes as my y values for my function. So if I graph this, it's going to look something like that. So a parabola going, part of a parabola at least. So what this means is, you know, if you're talking about the slopes, the object is going, the steepness is decreasing, and then it's increasing, coming back up. So these sections over here have positive slopes. So if you notice where I'm above the x-axis, so before 2 and after 6, the graph is rising because f prime is the slope of the line, actually. Okay, so example 4 here, sketch the graph of a function f that has the following properties. So f of 0 is equal to 0, so that means when x is 0, the y value is 0. The graph of the, so this graph is the derivatives, which means it's the slopes, and it's continuous. So I know that I have to go through 0, 0, and the slope here is -1, which means for every x value less than -1, the slope is -1. So that graph is actually going to do this. So down 1 over 1 coming this way until I hit x equals 1, because that's where the break is. After x equals 1, the slope is now 2, which means I need to go up 2 over 1. So the continuous just means that the graphs have to meet there at that corner. Because I could, if this part wasn't there, I could move this right-hand piece up or down wherever I wanted, as long as the slope was 2. It wouldn't matter. So that's my graph of the function based off of these pieces of information. It goes through 0, 0. The left-hand side has a slope of -1. The right-hand side has a slope of +2, and it's continuous, so it connects. Okay, one-sided derivatives. So just like with limits, you can have one-sided derivatives, so derivative from the right, derivative from the left. Because if you have a closed interval, you can't talk about a derivative because there is no other side of it. So example 5 here says show that the following function has left and right hand derivatives at 0 but no derivative there. So what I'm going to do is I need to find the derivative of this equation and find the derivative of this equation. If they're not the same, there is not an overall derivative. Just like with limits, if the left hand and right hand aren't the same, the limit doesn't exist. So for x squared, we're going to use so f of x plus h is x plus h squared minus f of x, so minus x squared all over h. And we'll do the same thing for this one. Limit h goes to 0, so f of x plus h is 2 times x plus h minus f of x all over h. So over here, that is actually x plus h times x plus h. When you have a quantity squared, 2 copies. So work the FOIL out. So that's x squared plus 2xh plus h squared minus x squared all over h. So the x squareds cancel. Whoops, forgot the limit. Limit as h goes to 0 of 2xh plus h squared all over h, which becomes limit as h goes to 0 of 2x plus h, and if h is 0, this just becomes 2x. So f prime for the left-hand side is 2x. The right-hand side, limit as h goes to 0, this is 2x plus 2h minus 2x all over h. So the 2x's cancel. Limit as h goes to 0 of 2h over h, which can be simplified again, of just 2. So this whole thing is just 2. So this is not that. So since the derivatives aren't the same, you don't have a derivative at 0, because the left-hand side and the right-hand side give you 2 different equations. One of them is 2x, the other one is 2. So not the same answers. And that brings us to the end of the section.